Sure. So Brian discussed a lot of the physical principles and other characters at play that we're going to be looking at. And so what I'm going to be discussing is essentially the inner magnetosphere. So we're going to start to see some of the applications of what Brian discussed and how it affects our day-to-day lives. We're going to start with the radiation belts. This is the first of 3 regions that compose the inner magnetosphere. In the radiation belts, we can find all sorts of solar winds and other extraneous particles that kind of just float about the atmosphere, float about the universe, because here they find themselves trapped and unable to escape the Earth's magnetic field. It is also here that we find 2 regions, the outer and the inner radiation belts. These are essentially giant donuts, toroids, if you want to be more scientific about it. They are trapped around the Earth, focused around the equator, and there's that slot region between the two. While we know it exists, the explanation as to why it remains debated, and there remain to be several theories floating about throughout the academic world. Oddly enough, if these particles, we do know that these particles can't get too close to the Earth's surface, because if the solar wind particles become too intertwined with our atmosphere, they begin colliding with the molecules, and they lose their energy, meaning that they can no longer qualify to be part of the radiation belt. Something interesting to note of this area actually is that these particles, despite their relatively tiny amount of mass that they have, the amount of energy they carry is tremendous. Because if you have a man-made spacecraft linger in this area for a bit too long, it can be rendered completely useless. It will be torn to shreds and completely unutilitarian. The next region that I would like to discuss is the plasmasphere. This is where we find what is known as non-thermal plasma. It's in the same region, the same area as the radiation belts, but this plasma is what I really want to start discussing with you. So you have these solar wind particles trapped, and they're bombarded by ultraviolet light and other rays coming from the sun and the rest of the universe. This interaction, this bombardment of the ultraviolet light rays and these particles rips free electrons. That is what ionization essentially is. So now you have these negatively charged electrons, and you have these positively charged particles that are remnants of this collision. This balance is what gives you plasma. What we see in lightning bolts is known as thermal plasma. That is not what we see here. Thermal plasma is where those positive and negatively charged particles are of the same temperature. Here, they're different. They're of different temperatures. It doesn't mean that it's any colder or any hotter. It's just a different interaction, a different form of plasma, and it's a way of classifying different parts of our known universe. The third and final region of the inner magnetosphere that I would like to discuss are the ring currents. This is where things can get rather interesting, because it is here that we find those solar wind particles orbiting around the Earth. These solar wind particles, they have a charge to them. And when you have something with a charge moving, it creates a current. It's not in the traditional sense that you and I are pretty much used to, with a copper wire and electrons flowing through it, but nonetheless, it creates a current. And that current induces a magnetic field. The induced magnetic field from this current is opposite to what the Earth's molten iron core creates naturally. So you end up with these weak spots. This is a map of the strength of the Earth's magnetic field, and it varies from day to day. But you can see how this ring current can have an effect. It's not a lot, but it's enough that it can be measured, and it will have interactions and change how our instrumentation works here on the Earth. Something I've been glazing over is how these particles are trapped within the magnetic field. I've been mentioning, they're just here. Well, how did they get there? And this can be explained with the introduction of polar cusps. These polar cusps are actually very similar to what you were talking about, Sarah, what you had asked earlier. These are essentially funnels, channels in which solar wind particles can be brought down to the Earth's surface. So you have the sun emitting its solar winds, and once they reach this polar cusp, they can find themselves trapped within that magnetic field and brought down to the Earth's surface. Because it's about here that the direction these charged particles are moving can find themselves perfectly aligned with the magnetic field. Because here, you don't have the divergence of the magnetic field because that's zero, but you have kind of like the fraying, the spreading apart of the northern and the southern poles of the Earth. So here, the magnetic field will apply either no force at all or very little. And it will find these particles, these solar wind particles, trapped, and they'll be sucked straight down close to the surface of the Earth. Now, you kind of ruined the fun of it all because the result of this is actually something quite beautiful. Because this is how we get the Aurora Borealis and the Aurora Australis. The Aurora Borealis to the north and the Aurora Australis to the south. What happens with these particles is that even though they're brought close down to the surface of the Earth, they keep all of that energy that they had originally. And so when they are brought down into our atmosphere, they begin interacting with the carbon. They begin interacting with the oxygen and the nitrogen in our atmosphere. This interaction results in the emission of light. It can be green, it can be blue, it can even be red. That's how we get the Aurora Borealis. This map here represents where the Aurora Borealis is at December, the 3rd of December, around 2 in the morning, Greenwich Mean Time. And so you can see just how that polar cusp creates a high enough density of these solar wind particles that you can see them here in the northern hemisphere. It's a very similar image if you were to flip it down to the southern hemisphere. And so, as beautiful as the auroras are to visually see with your own eyes, I think they're just as phenomenal to understand how they occur scientifically. It's something beautiful that the world gets to create for us. And so with that, I would like to thank my sources for making me sound smarter than I probably actually am, and I would like to address any questions that you may have. Yes, Max?
I'm going to probably botch my own question, but do you know what the distribution is for the types of particles in the radiation that you're speaking of?
So the radiation belts?
Just like, what is it composed of?
What are the particles?
Protons, yeah, neutrinos.
It's a lot of, it's a lot of just protons, electrons. I don't know exactly like the molecular formation. Yeah, I don't think it's.
If I'm not mistaken, outer belt is mostly protons, something as electrons.
Yeah.
But there are some.
There isn't a whole lot of difference between the two.
Yeah, there are some others, but
Yeah, there isn't a whole lot of difference between the two, besides like the density of the particles in these regions and the what was it? The composition and also the amount of energy that each of these belts contains.
Any other questions? All right, let's thank
And before you log out, I sent you my slides, so I wouldn't have to log in.
I had to